Hi there, this is another challenging topic. We're going to talk about polar bonds and molecules in this section. And this beautiful snowflake is due to the polar bonding between water molecules. So we're going to talk about that in this section. So we're going to use electronegativity values. We learned those a while back in an earlier section. Remember, fluorine is the baddest boy on the chart. It has a 4.0 in electronegativity. It really wants electrons. And this electronegativity number that you can just look at a chart and see who has low numbers, who has high numbers, really affect the way a molecule, once you have these atoms bonded together, the way the molecule, is it all neutral all the way around, or does it have a place on the molecule that has more of a negative side to it and then one with a positive side? So we can use electronegativities to figure that out, and the shape of the molecule. We need two things here, so this is complex as well. So if two atoms share their bonding, their overlapping clouds equally, then it's called nonpolar covalent. So they're sharing equally, nobody's stronger than the other, no one has a higher electronegativity number than the other one. That's called a nonpolar covalent bond. So if we have tug of war and each side is the same strength, then we have a nonpolar bond. But if one side's stronger than the other, then we're going to have something called a polar bond. So this example is hydrogen and chlorine hooked together, and chlorine is close to fluorine, so it's got a high electronegativity. So it wants to grab the cloud, or that tug of war. It's going to do tug of war and grab the electron cloud closer to itself. So it's going to attract that chlorine cloud, the electron cloud. So this side's going to be more negative because there's going to be more electrons over here than around the hydrogen. So this is going to be a polar bond, polar covalent bond. So this is where the cloud is not shared equally. So chlorine is stronger, it's pulling the cloud towards itself. Okay, so that's a polar covalent bond. So the more electronegative atom is going to attract the cloud towards itself and make a polar covalent bond. So we look at the differences between the two atoms. So for example, hydrogen has a difference between the two of 0.0. If we look at chlorine and hydrogen, there's a difference in electronegativity numbers of 0.9, so it's in the range of moderately polar covalent. Fluorine is that bad boy, so it really pulls the cloud, so it's going to be a very polar covalent bond. And if one is so strong compared to the other one that it can actually pull the whole cloud towards itself, then it's going to be an ionic bond. So this is how you can tell for sure what's going to happen between two atoms. So it's nice to have number differences, so this range is really helpful to figure out what type of bond you have. So if you have a list of electronegativities, it's super easy to figure out what kind of bonding you have. So that makes it nice. It's cut and dried. So what happens to polar molecules if they're between two oppositely charged polar plates? Then they're going to orient themselves to fit into the negative and positive side of those plates, and that is called a dipole when you have a partially positive, partially negative side of a molecule, a dipole. So when they're placed in that plate, they're going to orient themselves to be attracted to the right plate. So here they don't have any electricity. No, there's no electric field here. But if you have a negative plate here and a positive, then these guys are going to orient themselves towards the correct plate. So this side of the HCl is more negatively the cloud is pulled on this side, and so it's negative. So it's going to be attracted to the positive plate. And the hydrogen side is going to be more kind of positively charged, and it's going to be attracted to the negative plate. These little sigmas mean that it's not a full negative one and not a full positive one. They're partial. They're less than one. But they still have a slightly negative side and a slightly positive side. So how do intermolecular attractions compare with ionic and covalent bonds? So intermolecular attractions means between molecules, and they're weaker than either ionic or covalent bonding. So remember, covalent bonding is that sharing, that's really strong. Ionic is a plus minus attraction, electrostatic attraction. So those are strong. But now we're going to talk about some weaker forces. And these forces are responsible for what phase you have at room temperature. So this chemist, van der Waals, figured out one force called the van der Waals, we named it after him, the van der Waals forces. And this is a weak attraction. Another one's called dipole interactions, when the plus and minus side of partially positive, partially negative side of molecules are attracted to each other. So like the HCl, we'd have a negative Cl, the partially positive hydrogen attracted to another Cl. So these are between molecules. These are forces between molecules, intermolecular. That's a dipole because this HCl has a dipole. Dispersion forces are the weakest, and they're caused by just motions of electrons, so it's like a instantaneous movement of electrons in a bunch of molecules. So that's dispersion forces. So you'll need to read through this in the book because this is just a real brief beginning introduction for you. So please read the book about this. And the more electrons you have in a molecule, the more you can have dispersion forces, because the cloud of electrons can just move all over the molecule. Hydrogen bonding is what we were talking about in the water molecule. And hydrogen bonds have to have a hydrogen hooked to some other atom, and they make a partially positive side and a partially negative side. So water has a partially positive side and a partially negative side. So remember, this is partially negative oxygen and partially positive here, and that makes them orient themselves together in water. So that's why water has great cool characteristics. It has, you can fill up a glass over the top of the glass, and it will stick together because the water's kind of sticky. It likes to hook up or be next to each other by this thing called hydrogen bonding. So water has some really cool characteristics. And it helps keep the planet cool by this attraction. So it makes water bead up like that. And then we're going to talk about network solids. And I don't know if we've talked about network solids before, but these are solids where the atoms are covalently bonded together, and they have high melting points. So they're very, very, very strong. And so diamond is an example of that. You know, diamond takes a lot of heat to vaporize into a gas. We know it's a solid at room temperature because it has this beautiful structure of bonding together, carbon bonding in a network like this. So these are very, very strong things. Anything with a network solid. Silicon carbide is another example. It's a network solid, so we use that on grinding wheels and things like that. And here is just a characteristics of ionic and covalent compounds, just so you have that. So this is like a multiple choice kind of question in a test or a final. Like, what's the difference between ionic and covalent for properties? So let's try your quiz. So, in a molecular atom with the largest electronegativity value, what does it do? I'll give you a second. Alright, so it attracts electrons more strongly, and it gets slightly negative. That's like we were talking about the water and the hydrogen chloride. The chloride, it has a partially negative side. When polar molecules are placed between charged plates, the negative does what? So remember, they orient themselves towards, the negative orients towards the positive, and the positive orients to the negative plate, which is the weakest. So we need to talk about this more, but see if you remember which one I said is really weak. So van der Waals is really, really weak, and we'll talk about that later. This is an introduction to all these things. Not an easy section, so we need to talk about it more. Alright, I'll talk to you soon. Have a great day. Bye-bye.